seminars. I'm happy to be back in Denmark, even in this virtual way. I would be happier if I was there visiting you, but I hope that this can come soon. And I'm actually very glad that you and Nitish invited me, because I think it has been a marvelous series, and my students have enjoyed many of them a lot. So thank you very much for organizing. So in the last years, my group has started to work in this broad area of artificial photosynthesis. I mean, the reasons for that, everybody knows, so I will not enter into the details. There is all the problems that we have been facing with climate change, and all the problems that we have with the depletion of the future fossil fuel resources. And actually, we were lucky enough to get resources from the European Commission in different ways. I mean, with going from the ALIF to the different programs in order to get us started. And I have to say, because Karen told me at the very beginning, you can explain about your own situation. I was really scared at the very beginning to enter this field. And the reason for that was that there were very many groups working on this already for many years. And actually, I thought that we were a little bit late on this. So the whole idea about using light and renewable resources to get chemicals or fuels comes back since many years ago. And one of the typical explanations for that is it's typically said by Chamichian, who wrote this fixed solar energy through treatable photoelectrochemical reactions. All of you know that the energy stored in the hydrogen, in the water molecule, can be splitted, and we can use this chemical energy in the direct or reverse way, depending on how we need it. And this is the way we will need to go in the future in order to accommodate all the needs we are having. So when I was in Denmark, actually, it was Jens Norskov who started to do all these electrochemical modeling. And that was with Jan in this early paper from 2004 that they started to use the chemical hydrogen electrode. So being able to establish a theoretical framework in which we could calculate the reaction processes that were going on electrochemical devices was not so straightforward. And it took a little bit of a while in order to get all the fix for the equations and all the model right. But this has been an extremely successful model that has been working for the last 20 years. Of course, it has approximations. It uses only thermodynamics, the pH and the potential are introduced as linear corrections. And many of you have seen that most of the time what we are using is this proton-coupled electron transfer that simplifies our lives. In our particular case, we have mostly working with PBE as a functional, and trying to explore also these semi-continuous or continuous models for representing the solvent that were extremely common in homogeneous catalysis, and we try to have ourselves our own model for these two. So the ultimate thing is that, okay, you have a cycle like the one that is shown here. I don't know if I'm pointing right. So basically that will be for the oxygen evolution, and in here the two different parts are marked, one in black and one in green, and I will concentrate only on the one in black here. Actually, this is the report for one of the papers from Jen saying, okay, then we'll have the thermodynamic step for each of these steps, so for each of these intermediates here, and actually the one that is the most deviating from the ideal behavior, that will be the potentially determining step for this particular case. And by doing so, what you can do, and this is a picture from the times that we could fly, actually, this is the Etna mountain in Sicily. Actually, you could draw one of these very nice volcanoes, the stabilization of the whole reaction system. And the top of the volcano was marking the overpotential within the same mechanism or the same compound family And actually reaching a point that it's on the top of the volcano, that's more challenging, because inside the volcano you can always optimize. Outside of the volcano, you have to look for different ways how to get different linear scaling relationships or linear different dependencies between intermediates. I will come back to this later. So actually today, because of practical things, I will start with the CO2 reduction, and then I will go to the oxygen evolution reaction. These are the two parts of the device. So you know that in one part you are doing the oxidation, and in the other part you are doing the reduction. And actually reducing CO2 will solve two problems. First of all, we will reduce the amount of CO2 that we are having, or we will have a CO2 neutral process. And then the other thing is that it will allow us to go through processes that we know, or through compounds that we already know how to deal with them. So I will start by this. And one of the main things that we have been considering is that we would like to do all this chemistry with simple materials. By simple, I mean earth abundant. And the list of earth abundant materials is not that large, but one of them is this copper. And as you can see, copper here is this very nice piece, and has a little bit of oxide, which is marked by these small green areas, for instance, this part here, okay? And this will come important later on. The thing with the CO2 reduction is that you can actually do far too many things at mostly the same potentials. So contrary to what we typically do with the oxygen evolution reaction, you end up having, in the CO2 reduction, you end up having simple molecules containing only one carbon atom, but you can go from formate of formic acid to CO, and from them you can start making C2 products, or even larger products, but all of them, they come more or less in a very narrow range of potentials. And then the overall problem is that selecting one of them is the most difficult part, okay? As you can see, the gain here that we will have for the different products will be extremely different. So that makes selecting the right product makes really the difference for the process to be more or less suitable for commercialization in the long run. So when we started here, that was the understanding of the different competing mechanisms in CO2 reduction. The whole idea is, well, starting by the surface, you could trap CO2, and I'm not sure that I can mark what I'm doing. So, okay. Let's see. So you could go this way here and trap CO2, and typically this route was understood as forming this intermediate here, because it was taken as a proton-coupled electron transfer. And then eventually from here you could go to formate, taking another proton and another electron. Or alternatively, you could go the other way around, putting the proton and the electron on the other side of the oxygen, not on the carbon, break the bond, make CO, make water, and revert to the surface. Of course, to this, there is always a competing reaction, which is the HER. So that's a hydrogen evolution that will be competing with this system here and creating some of the problems that we are facing in the selectivity issues. This is very early results by Jens and Andrew Peterson, and that was really an amazing, nice work for 10 years ago. So that was, they were working on the CO2 down to CO path for copper, and showing that there is this problem with the hydrogen. And actually, a little bit later, Jan and Jan Roos-Meisel and Peter Strasser, they were separating the different metals depending on how were the binding energies of the two most crucial issues, so the proton and this intermediate here, in order to know what would be the main selectivity to the different products. So that was the state of the art when we started to work here, but actually I want to trace it back to what is in the in the books in chemistry. So as a chemist, for me, CO2 is a closed shell molecule that has 2 double bonds. So this means that the activation of this molecule is extremely expensive. And this is what this tries to see. For us as chemists, activation means that you are able to fold these bonds. So this is the alpha bond that is between the oxygen and the carbon. It's here, so this one here. And being able to fold it means that you will be able to do some chemistry afterwards, okay? As you can see here, if I don't transfer any electron, because this is 2 double bonds that are one close to the other, the energy that you need to force this bond to be bent is extremely high. This is in the order of 3 eV, just to make it 120 degrees. So actually this can get easier provided that you are putting some electrons into the system. And actually you can see that only for 1 electron, this already goes down to 1 to fold it up to 120. And more or less it's the same for when the system contains 2 electrons. So actually this is one of the crucial issues, is that CO2 is so rigid and that it's so inert that actually you won't be able to activate it unless you do something really clever to the system. And actually this can be done in a different way. For instance, this is well known that if this carbon has already another bond and I put a sulfur here, and the reason will come later, then what I can do is actually folding this bond is much, much cheaper. So actually, if I'm able to tether this molecule into something on the surface, maybe the opportunity to do some chemistry here on this part of the materials is in this part of the compound is easier. Okay, but that's in the books, and this is why the talk is told about chemistry and in electrochemistry. So the whole idea was taken by Javier Perez Ramirez and others, and they were trying to dope copper with easy stuff. Okay, so easy stuff means just one atom of this part here of the P block to see if they were able to see something different. And actually they did. These are the different materials that you could generate with sulfur, selenium, and tellurium. And actually when you do this, you see that these materials are incorporated. So actually that the secondary, this dopant atom is incorporated into the material. And the thing is that if you incorporate these very little impurities, the whole profile changes. So this will be a copper system derived from an oxide, and I will come later to this discussion. This is with sulfur, selenium, and tellurium, and you see that you have a different distribution for the products in this particular case. And what is most important, I have shown you before that for copper alone, the main product was CO together with hydrogen, and in here it completely switches to formate. Okay, for these materials here, this is at the voltage of 0.6, and this is at the voltage of 0.8, but this is not so relevant here. And you can see that these kind of profiles, they have the shape of a volcano that we have been discussing before. Actually, what we did was trying to see what was going on with this type of systems. And actually sulfur and the other elements from the same column, they are actually adsorbed on the surface, and they are partially polarized because the copper is already delta minus. We are putting some potential, so the atoms adsorbed here are also very much delta minus. And what you can actually do is trap the CO2 in this same way that I was explaining before. So trapping the CO2 in an activated manner that leaves all the system a little bit more prone into reactivity. And if you do this like that, then you can pass a proton and you can pass an electron, absorb it on the surface, and make the formate go away to the solution. Actually, there is an alternative path that involves the absorption of a proton and an electron in this heteroatom first, and then a Herovsky process that can go this way just by the CO2 that is approaching the surface with the hydrogen here and getting the hydrogen and evolving deform it to the surface. Okay. So actually, we check what was out of these two paths. For the two paths, we check how was the different dependencies of the Gibbs energy for the different intermediates here, and also in this second path here that I have shown you. And actually, in both cases, if there was some oxygen remaining, this will not be too effective in order to evolve the formate here, because this is in this part of the volcano, and it's the same here as in this part of the volcano. So actually, we would like to sit in this position or around this position for this mechanism, and around this position for this mechanism, because this is the G for evolving hydrogen. So you would like to be as close to here. So basically, the atom that is the best at doing this corresponds to the sulfur in all this family of oxygen, sulfur, selenium, and tellurium. So, but as you have seen, I mean, I have lots of materials, and then this material that it's called the oxygen-derived copper. And oxygen-derived copper is an extremely complex material, because typically it is prepared in a way and then it's put under reaction conditions. And this is the second part of my talk. Actually, sometimes in order to get proper performance, and by proper performance, I mean enough current and enough products, the systems are placed in a way that you prepare the material, you put the potential, and you want to use these gas diffusion layers. And this is the configuration that you will try to use in order to get the maximum productivity of the materials, okay? The problem is that we don't know the intrinsic nature of this oxygen-derived copper. So in this part of the project, what we did was to start with materials that were derived from copper, and some copper oxide, I mean copper oxide here, or some copper oxide on top of copper. And the whole idea was to see if we were seeing something particular about the reconstruction, okay? We know which are the typical patterns that we need in order to get C2s, and this has been very nice work by different groups. But the problem is that are we sure that this is the only kind of shapes, or only copper is on the surface? Is there any oxygen left? So what we did was to take these two models, make this type of reconstructions where we were eliminating some of the oxygen atoms from the surface in these three different motifs, and try to see what was happening there. And I have to say that this is an extremely rough model, because we are applying periodic boundary conditions. So in a way, we are limiting the size of the potential reconstruction. Then the number of atoms on the configurations, well, we try to use three different shapes in order to get an idea if there were significant differences between the different initial patterns, okay? That would be like heating, that would be like grain boundaries, and so on. But the whole idea was to see, and we don't have electrolyte or solvent in these simulations. So these are extremely simple simulation, and the only concept behind this is try to see if there are some new ensembles that are different from the ones that we could expect from a copper 111 or a copper 100 surface, okay? So what we basically did was run these molecular dynamics. We put a little bit of temperature, because otherwise, you know, these are slow calculations and pretty expensive. And actually, we did run these different systems for about 10 picoseconds, okay? All these 6, 7 systems in different ways. The whole idea was to see if there were some common structures that we could trace back to these different systems. When we did that, one of the first things that we did was to check with a kind of Pouvet diagrams if the energies of the structures that we were constructing were reasonable, okay? And this was done through the different structures, checking that the energy per unit and the relevant conditions, let's say the normal potentials that we were, that are applied and for these systems, and the regular pH that we can expect on the surface were not too off from the rest of the materials. We also check at this point how was the stability for the different oxygens at different pH, okay? And you can see that even for remarkably important potentials, so let's say here minus 0.8, depending on which pH you are using, some of the oxygens could remain in our system, okay? This is just to check that the model is robust enough so that we can say at least something. So when we did that, this is one of the typical movies, and let's hope that this works now. Oh. So this is the top view of one of the reconstructions, and the atoms are labeled like this, are colored like this. So basically, if you have a copper atom with 2 oxygens, this is the oxidized copper. Then you can have a polarized copper, so a copper atom that it's close to an oxygen, but only close to 1. And then you have metallic copper, which is basically surrounded by the rest of the coppers. This is the top view. You have the rest of the things, and you can consult all these videos because they are uploaded into our database. So this is the top view, and you can see that some of the atoms, they reconstruct, but whatever you do, you end up having patches of these copper-like species, polarized copper, and the oxidic coppers. Okay, so this is the side view of the thing. So you can see that the changes in this case are mostly on the outermost surface, but you cannot completely discard small changes all through the thickness of our layer. So yes. So you see that every now and then some of these atoms, they change color. Actually, then what we did was to take the snapshots, different snapshots for these very long simulations on all these systems in order to try to figure out if there were common patterns in the material. This is what we will have in the next slide. In order to do that, one of the things that we did was to analyze the radial distribution functions. The other one was to check for the Bader charges. We know that Bader is not the best way to obtain a charge, but at least it was a proxy for the real charge or for a close enough charge for the material. And also some geometric patterns of the different reconstructions, depending on the first neighbors and second neighbors of a given atom. Okay? And this is what I will be showing when the movie finishes. Okay, so yeah. So these are the 3 things, the 3 main patterns that I was telling you. Basically in this part here, okay. In this part here, what we were checking was the radial distribution functions. These are 3 different models, okay, the models described before for the reduction system and for the system that is started by the oxidation. You can see that this one seems pretty much a constant, so we don't see very many changes depending on the initial starting point of the material. So that's why we took only one of them to make the analysis, but you can take a look in our work because there are all of them. And actually, when we were calculating the charges for the different atoms here, you could see kind of 3 different families. 3 different families with very distinctive charges, and this is why we could make the plot that I was showing you before. And also, this kind of charge is a sign, it's very much correlated with the number of copper-copper bonds that we were having, okay? And we could see that there were really, when we were calculating as a density, we could see spikes for the given coordination number. So that gave us the idea that basically we could collect all these trajectories from the MDs for the different systems and try to figure out if there were special ensembles, okay? The way to categorize the ensembles was done with the previous slide together with this one here. This one here is showing just angles for a particular given species with different atoms. And once you do that, actually you end up with a collection of systems that has been summarized here. You have copper atoms, you can have some different types of facets resembling the 110 or the 111 or the 100 surface. You can have areas where you have oxygen systems, or the oxygen is close to the surface, and you can have some other ensembles of different kinds that are motifs. Of course, the different weight, the different number of these motifs, the different density of these motifs will depend on the initial structure and the total oxygen remaining in the system. But it's significant that after all these MDs, with all these constraints that I have said before, there is we can still make a group and make a simplified model of how this goes. Okay. Actually, what we did later was, okay, now we have 14 more ensembles. What is going on with the reactivity on these ensembles? Is there anything particular about that? And of course, for some of the materials, we were just seeing that trapping CO2 is just as expensive as this used to be. And for some others, it's significant that the binding energy for CO2 is very, very strong. And this is related to the position, to the existence of these subsurface atoms or near surface oxygen atoms that are trapping CO2 as a form of carbonate, which had been reported in the literature and that we were obtaining in a very, very simplified manner here. The other remarkable thing is that this delta G for the adsorption of CO2 goes as a straight line, more or less. Okay, we have some deviations, but it goes very closely with this Q. And the Q here is the polarization of the site. Okay, so for each of the sites that I have shown before, we calculated the beta charges and we add them without the sign just to get to know how polarized this particular site was. Okay. Again, we try to do this not only for CO2 to see the CO2 trapping, but also to see the carbon-carbon bond formation. And this is where one of the surprises came. Okay. Again, the Q here represents the polarization of the site. In this type, the site is a little bit bigger because it contains the two different carbon atoms. So we are aiming to form this carbon-carbon bond. And you can see that the typical structure that was reported in the literature is this bunch of red points here. So basically, they're expensive to form. Delta G's are positive. So these seems that in some cases, they are even very positive. So these seems, they don't seem very effective at doing that. On the other side, you are forming what is called a glyoxylate, what is formed an oxalate in chemistry. An oxalate is, in chemistry, is that you are coupling two CO2 molecules. And actually, these intermediates are very stable, and they can be also important into the elimination of copper atoms from the surface, okay? Because they are very good chelating agents, as the chemists call them. But right in the middle, where these two close, and where they, when the reactivity seems very close to, the delta G seems very close to 0 for the reaction, we find this kind of intermediate that has a CO on one side and a CO2 on the other side. This has a chemical name, and this is a glyoxylate intermediate. And we think that one of the parts of why these systems could be so effective, these oxygen-derived copper materials, is because of all the reconstruction, they are able to form these kind of structures that are extremely polarized, very stable, and for which the thermodynamics are really very, very close to 0 in order to form the carbon-carbon bond. This is further reflected into the kinetics. So we calculated, and this is without bias or without anything, the simplest climbing in image calculation that you may think of. And actually, the glyoxylate, it's this one, the lowest one here. So actually, it seems that also from kinetic point of view, this seems a suitable path. Actually, when we saw this, we were really surprised because it has been proposed in prebiotic chemistry that these kind of intermediates with a CO and a CO2 could be relevant intermediates in order to make larger molecules in prebiotic chemistry. Okay, so much before enzymes were done. So I think that this is a promising way to go, and maybe we need to spend a little bit more effort working on this kind of alternative materials. Of course, this is not finished, because solvent effects, cationic contributions, larger reconstructions, they will, all of them play a role. And for sure, the proper calculation in the way that Karen does of the reaction barriers and of the thermodynamics with all the potential include self-consistent in the calculations. So that was the talk that the student made for this particular thing. Okay, I mean, it's a little bit too girly. On the other part, so yeah, now we have another idea of how the C2 can be built. Probably it's complementary, probably it's an alternative route. Maybe it might be the dominant route for this oxygen derived. The other nice thing of oxygen derived, and when you are working with gas diffusion electrodes, is that actually you can go farther than C2. And going further than C2, forming higher alcohols, that would be very much demanded by the industry. So in this work, we work with a group of Javier Perez Ramirez in ETH, but also with a group of Yale in Singapore. And actually, they were able to, starting by CO2, end up in the acetaldehyde and end up all the way in butanol here. And as you can see, the amount of butanol, well, it's small, but it's present at these potentials, which are not so large. The results are extremely consistent, but you need these gas diffusion electrodes and oxygen-derived materials in order to be able to see these things. So basically, the problem here starts to be a little bit too large. And this is why in the group, we have recently started to go a little bit beyond DFT, because with DFT, we know how many calculations we can do in one day or in 1 month. But these reactions networks start to be very large, okay? So we have an automatized way of generating the molecular graphs and the different structures for all the intermediates going from 1 carbon atom all the way to C4 or higher. We have developed a graph isomorphism in order to not to calculate more than once each of these steps. We have a labeling interface in order to make it work with some labels so that we can store all the intermediates in an easy way. And actually what you end up having is a system like this one here, which this is each of the intermediates that we can have, and this is only for one potential alcohol. And actually the color code here is related to the energy, and the lines here are related to the connections between the different intermediates at the different points. Okay, this can be summarized in nicer plots, and actually I'm glad that we can have these nice networks now, where you can see the intermediates are marked by triangles and the transition states are marked by circles. And actually, the closer you are to here, it means that the lower the energy will be in order to do that. And so this is work that Sergio Pablo Garcia has been doing in the group. But still, we need to work more on this, because these are the reactions that we are calculating on the surface. And actually, a couple of years back with Rodrigo Garcia Muelas, we were able to calculate or get a proxy for the adsorption energies on different atoms using a principal component analysis that allows us to estimate the energies in a very cheap manner. Okay, for all this for different metal systems. We are trying also to spend that, and actually I was extremely happy when we did that, because we found that out of these principal component analysis for the adsorption energy of oxygen containing intermediates on the surface of different metals, the first term that we were finding was a D-band. So all goes back to the old models by Jens. The second term that we obtained in this principal component of, analysis was a redox term that was the second one contributing. Okay, so these are the first term and the second term for the metal and for the adsorbate. To know a little bit more, and the reason for that is that we have typically considered reactions on surfaces, but actually in the last years we have also seen that the situations might be more complex. And when you have solvents, one of the typical reactions that you can have is a reaction in solution. And this is something that an organic chemist will tell you. This is what is called Aldol condensation. So if you have this kind of molecule here with a double bond, with an actual carbon-oxygen double bond, you can have the reaction catalyzed by protons or by OH on the solution. And actually by taking two, you can make this carbon-carbon scaffold. And this is an alternative way to go to higher alcohols. So actually when we did the simulations, we ended up having the following. Once you have the acetaldehyde form, the condensation takes place in solution, and only the protonation or the hydrogenation of the products down all the way to this intermediate here, and then all the way to 1-butanol was going on the surface. So you have this combined chemistry from the solvent and on the surface that is acting in order to make these higher alcohols, higher carbon number alcohols. So I think that this is also another take-home message. I mean, we can make our reaction networks very nice and very complex and summarize the energies, but then we need also to take into account what is going on in solution, or for some reactions that we have done in the past in the gas phase, in order to get all the chemistry right, because it might happen that not everything is happening in solution. Actually, for the 1-butanol, we ended up finding out that there was a possibility to increase the Faradaic efficiency for this particular material. And contrarily to what we are used to see, which is the volcano plots, where you have one point, a very continuous dependence that goes up and then goes down. Actually, selectivity problems are characterized by this cliff nature. So basically you end up increasing, and then at some point everything goes wrong, okay? So this is, yeah, you can only do these things for some of the materials, and actually here, basically you're having an oxide that it's covering part of the surface even. So you cannot improve the formation of the butanol more than that, okay? So, and as I expected, I will have to go relatively fast on the second part of the talk. And this is everything that I had for the CO2 reduction. I will go to the oxygen evolution now. And on the oxygen evolution, we have seen all the work that everybody had been doing in the very many years, and actually there was this very nice paper where Max and Alex were working with the detergent, and when all of you were still in Suncut in Stanford. And actually, these systems were extremely nice because they shown the potentiality of going from 2 metals to 3 metals and go all the way to go get more than 3. The only problem here is that cobalt is a little bit, it's listed in some places like a potentially critical raw material, okay? This is listed every now and then in the European Commission as a potentially, a potential material that might not be enough if we want to use it for all the batteries that we would like to. And so our colleagues at ICIQ in one of these programs, they started to do some reactions on rust. Okay, and rust is this beautiful thing, which is basically iron oxide that you can dope with different things. And people had been doing this for ages, so we were not the first ones. Huh? And basically, if you were doping with nickel, starting the reaction here, iron oxide, which is not very good because it has a very large overpotential, you could reduce the overpotential for the oxygen evolution reaction. And the dependence with the amount of nickel in this part was, okay, I mean, not very large. This part around here is about 4%, okay? The problem when it decays is that basically it starts populating the bulk of the material. And actually what they did was to look at the places where people had not been looking, okay? And this metal here is zinc. Most of the works that have been done related to this, or every time people was thinking about, well, if I'm doing a redox process, then I have to add a redox active species in order to make it more redox active, okay? And in here, it turned out to be a little bit different because actually when they used something that was not redox active like zinc, the activity was growing all the time, okay? And it was growing so nicely that it was growing up to the point that the phase was changed, okay? For an 8%, you change the phase of iron to the spinels family. So actually what we did there was to see if there was a possibility for a mechanism with two different sides, okay? I will not go further into this. Actually, these were the points with all the redox active, and this is a standard plot with the OH as a function of the OH that you have seen lots of time. That line here would be the ideal, and actually by doing parts of the reaction in the iron part and then the other parts in the non-redox active, one was able to reach this point here that correspond to the experimental overpotential that they were measuring. Okay. So non-redox might be a little bit good in some cases. In some other cases, and this comes to the well-known system of the nickel oxohydroxide. Maybe some of you know the story, but basically these materials are known to capture some iron from the electrolyte. Electrolytes are very difficult to purify, so you end up with systems like this ones. So nickel, it's likely to form lamellar structures and incorporate some iron. And actually when you do this, then in this particular case, yes, you have this redox term coming from the iron that can be adapted to each of the configurations that you are doing. And for this also we did some molecular dynamics. The take-home message is that you end up with a much lower overpotential, and the reason is because this inducted redox term, they can balance up to the point that you are needing. Okay. So these materials, they do work. They are difficult to obtain, and this would be a kind of material that would have been extremely difficult to predict from a theory point of view, just because we have never thought about these kind of structures with atoms coming from solution and so on. And because they are difficult to obtain in a regular, homogeneously distributed manner, even if they have overpotentials, probably we will not be able to go much further than that. They don't seem as the best possible solution ever, particularly because you can not produce as much current in some cases as you would like to do, okay, because of this inhomogeneous distribution coming from the intrinsic disorder. So this takes me to the last thing that I wanted to discuss, and this is the oxygen evolution reaction, the magnetic enhancement that you can have in the oxygen evolution. So this is a very particular case. Again, we were working with the group of José Ramón Galán Mascarós, and actually they were playing with a magnet, and for one particular conditions of the reaction, and this comes up to be extremely important. So you have seen this plot before. This is the two reaction, the external part, which is the one that I have discussed for the other mechanisms. This is a water nucleophilic attack, but there is also this possibility for this surface recombination, okay? And these are the experiments, so you can see that the magnet, there is nothing special about this magnet. They were just putting it close here. Actually, we did lots and lots of experiments to show that there was not any inductive or any problem with the cables that we were using, that there was not any problem related to the use of 2 or 3 configurations in the experiments. I mean, that has been a real tough experiment, but actually what you see is that the given potential, when you have the magnet, you go much, much faster, and you produce much more. So the amount of current that you can have is much larger. So the magnet is relatively small, and the pH is important because the pH ensures you that you mainly go through this route here, or at least that this path contributes. The way we understood that was the final chemistry issue that I want to point out, is that this material here is an antiferromagnet. And if you use an antiferromagnet, well, and you try to couple oxygens, then you will end up with an oxygen that is a singlet. But actually, the ground state of oxygen is a triplet state. And the difference between the singlet and the triplet state is 1 eV. So if you would like to go this way, that would be painful. Huh? With the magnetic field, we are aligning the nickels, or one potential explanation is that we could align the nickels and then go all through this way here. In this way, we will produce a low energy oxygen in the triplet state. In this case, this is just one of the potential representations, and that could be a potential way why these type of configurations could go to cheaper paths and produce a little bit more, because the relative weight between these two configurations will depend on the presence of the magnet. Of course, you could use temperature to do the same thing. We have seen, we have still lots of experiments to do to see how is the interplay between the temperature and the magnetic field, and if this is the correct solution, or there might be other things coming from the electrolyte or other magnetic effects. Okay? With this, I just want to make a summary saying that, well, all the advanced processes that we are aiming at, they will need to rely on how to avoid, how to circumvent, or how to find clever ways of breaking the linear scaling relationships, okay? This is just a list that we put a few years back, and as you can see here, there is the magnet here with the external forces, but there might be other clever ways of making the systems a little bit more active and or significantly more active, and for sure significantly more selective. So as conclusions, I hope I have shown you that there are many chemical effects that we have considered that are needed in order to understand electrochemical processes, and the more we see, probably the more there will be. That some of the materials can generate new intermediates and might have a role in these electrochemical processes, and that maybe we can control these new routes that we haven't thought before. That the adsorbates, coadsorbates, and solution chemistry, decoration materials, solution chemistry, they may play a role when we are studying these very complex reaction networks. That we have to be careful and explore, because non-active impurities like this zinc may enhance the activity, and that experiments, they always have impurities, and we need to know a little bit more about what is the chemical role of these impurities in the systems. And that maybe in order to reach performances that could be useful, we will need to think a little bit out of the box in order to get, for instance, with external forces, to performances or to currents that are more amenable to practical use. And with this, I would like to thank the group, the Barcelona Supercomputer Center. It would be impossible to do things. All our structures are here in the IOChem. You can go download and play with them. I would like to thank my collaborators, Yeo and Perez Ramirez and Garan Mascaros. We have been discussing very many things in this very complex field, and I feel fortunate to work with them and to work with the group. And for many of you that don't know this cartoon, well, we don't have super heroes here. So they in Spain, they ended up having this super Lopez, which is this small drawing here, okay? And it's supposed to have a super group. And as you can see, this is the standard way how the group works. So, and thank you very much. And I will take any questions that you may have. Thank you.
Okay, great. Thank you so much, Nuria, for that really interesting talk with so many different topics that are very, very relevant for us. So I would invite you to either use the chat or to just put an X, and then you can unmute yourself to ask your question live.
I have a question.
Oh, there's Jens. Okay.
Yeah, beautiful stuff, Nuria. I like this magnetic effect particularly. What kind of fields are we talking about? Are they manageable, or is it only something you can do in a well-equipped lab?
So this is a $10 magnet that you can buy over Amazon. 400 millitesla. Nothing special.
Okay.
That they just had it in the office and they just played. Tell you the truth. Of course, the field matters, the orientation matters, and we are trying to see if it would be possible to incorporate this in a device.
That was exactly my question. Okay, thanks.
Yeah.
I wonder if I can follow up on that, because that's a really interesting idea. It's just the effect seems to be really small for something that involves like a switch and spin. So is there a way that you can increase the magnitude of that? Or is there something wrong with this intuition that like if you're...
No. I think so. One of my first questions to the experiments was, okay, can you try different materials and see if this effect is different for the different materials, and we can correlate with the transition, the critical temperature or something like that. That would be the obvious thing. If you keep the magnet strength, then you change the material. Well, it was not so straightforward to do that. And we have seen that there are some effects going on with the temperature. So yeah, in the preliminary results. The problem has been that we haven't had much more human power to follow much. Yeah, but I mean, playing with the different strengths, playing with materials with different critical temperatures for those lengths, that will be the next follow-up. And it seems that people is claiming that this could happen also for some other systems related to CO2 activation. And in there, I'm a little bit more skeptical. Mm-hmm. If the spin is the controlling term. Mm-hmm. So if there are some other terms, magnetocurrents, distribution of the electrolyte close to the surface, or some other thing, I think it's something that we need to really work on it to see if we can push it farther, because this could be a way.
Yeah, interesting. Thank you. Yeah. So if that's the case, then I can just go on.
No, there's a...
Oh, really? Oh, wait, there are questions. Oh, Gaston. Okay, please, yes, please unmute yourself.
Yeah. Hi, Nuria. Thanks a lot for the talk. I have a question. I was wondering whether you could comment a bit on the lifetime of the effect of the oxide-derived copper. Basically, I mean, once all the oxygen is removed from the material, are you still going to have these ensembles? Are you still going to have these different copper species on the surface, kind of leading to this different reactivity? Or is it very much depending on, you know, having material that does have oxygen in it?
So this is extremely painful but interesting question. So one of the things that pushed us to investigate what was going on there was the fact that the product distribution depends over time for the oxygen-derived materials. So this points out that you will have different contributions or different examples. I would tend to say that yes, once you are exhausted, it would seem that you will reach a steady state where you will have as little oxygen as possible if you are pushing the potentials very high. Okay, that will be my first answer. But there are two things to this. First, from the calculations, it seems that the window at which you will have some oxygen left is larger. So you could actually have a kind of equilibrium with the solution to have enough oxygen around in the surface layers. That would be because the thermodynamics seem to point that they are still okay. Then The other thing is that if you're pushing a lot, okay, in the potentials, then you will end up in a place that it's quite disordered. So the copper there will be quite disordered. Even if it's metallic copper, if you have exhausted all the oxygen, which I'm not completely sure.
Right, right. Yeah, interesting.
Okay,
Thanks a lot.
so there are at least these two things yeah, I mean, steady state, it's always meant to see that you have a constant production of products. Huh? So in principle, this could be reached even if you take days. But the material left would be extremely disordered compared to the things that we typically have in mind.
Right, thank you.
So what, okay. Oh, Mega?
So slide 11.
Yeah.
So the question is, how would the graph on slide 11 look like if you would transfer 3 electrons to CO2? So I think you showed from 1 to 2, there's not much of a change in the delta E, right? Oh, she can't go.
Okay.
So can you hear Nitish?
No,
Sorry.
I cannot.
Oh.
Slide 11, is this one?
Yeah, slide 11.
How would the graph look like if you were to transfer these electrons to CO2? Okay, slide 11. Let's go to slide 11. Can you see my slide?
No, don't think so.
Okay. So this is slide 11. Actually, the electrons are transferred to CO2.
Yeah, so I think the question is, can you go to 3? From 0 to 1 to 2 to 3?
They will not make the difference. I mean,
I think that's the question.
we are saturated.
Yeah.
Maybe, I mean, here, no, it's the same.
Yeah. Okay.
Well, basically, it means that you need to start populating the anti-bonding states. And once you populate one, it doesn't matter. I mean,
yeah.
The next ones are degenerates. So basically, you don't see much more.
Yeah. So I had a question. So the last slide that you showed, which is all of these different ways you can break linear scaling relations. So I was wondering, so in the long term, I mean, so one can stabilize OH relative to OH. That's one way, and I guess the other way is to switch the mechanism itself in a way that, for instance, you go to radical oxo coupling or something. So I was wondering if do you prefer one over the other, or do you think that they're both ways one can get to a better oxygen ablation catalyst?
Well, I have to say that for the oxygen evolution, I have my doubts that we will get better than these 200 that we are already getting. I'm sure that there will be particular cases, but I'm not sure that we will, because then it would be similar to what is happening with the hydrogen evolution in this very nice paper by Andrew Peterson, that he's saying, okay, delta G is no longer good when you're at 0, because you might be, then you will have the kinetics kicking in, that we are typically not considering because we think that the thermodynamics suffer. I mean, suffice because they are endothermic enough. Yeah. So I would say that I'm not sure that we can get much better off on this side.
Let me just point out, we disagree with Andy Peterson on.
I would like to hear from you what we can do, but so I will be very happy to hear more on this. I would say that depending on the particular reaction that you are checking, the OOH, I mean, making a hydrogen bond seems a very good option. So any kind of decoration that could help you making a hydrogen bond, that will be a potential way to go. And that would be, I mean, to me, that's the obvious solution. switching in a very defined way that the oxidation state of the atom will do a reaction, that's also a suitable way for some of the things that we are seeing. And that reduces a lot the potential that you need for activating some of the things. So this is the case of CO2 on nickel on these carbon, nitrogen degraded carbons. I mean, just by finely tuning, you end up with the right nickel state, and then in there you need less potential, in principle. But synthesizing in a useful manner these materials, that will be extremely difficult.
Yeah. Great. Let's see if there's, yeah, Karen, I think.
Yeah, so maybe I can ask a question to follow up on Gaston's question. So if I remember correctly, you have some kind of thermodynamic analysis and then you have some dynamics. And from the thermodynamic analysis on these oxide-derived materials, it looks like only copper is stable under reducing conditions, right, in the Pourbet diagram. Or is that, am I reading this correctly, that when you go like below 0.1 volts versus, well, I don't know, I have to do this.
Yeah, this area here, you mean?
Yeah. So what would be the window where you expect oxygen, at least from this thermodynamic analysis, and then afterwards you have all these dynamics, which was super interesting.
Yeah, I mean, this is the window at which we were doing the experiments.
Okay.
CO2 reduction. Yeah, even with the sulfur, I mean, this minus 0.3, 0.44, something like that, and this around this potential.
It's 0.4.
Now the problem with these Pourbets or the thing with the Pourbet is that in principle you are putting everything is order and everything is nice. You don't have errors. You don't have configurational entropy. You have I mean you have pure thermodynamics.
Right.
I would say yes, probably the window for the oxygen to be there is slightly larger than it's in these plots.
Yeah, because then you have all this dynamics, and from what I remember, you have a pH-dependent oxygen population as a function of RHE potential.
Yeah.
How does that arise? Because I often think of oxygen stability as determined by an RHE potential. So how is it that they're all so how does this arise?
So these ones are derived from single point calculations and some of the structures.
Okay.
So I mean, this is just a simplified way to see that from the thermodynamic point of view, we will still have some at these given potentials.
Okay.
Of course, this relies on the outcome of the simulations after the relaxations with the molecular dynamics.
Okay. Interesting.
So there's, I think, another question on the molecular dynamics. So the question is by Carla Banyak. And the question is, I was wondering about the dynamics of the layers lower than the first surface layer during reconstruction of oxide-derived copper. It seems that there is also something happening in these layers based on the side view videos you showed.
Yeah, well, I mean, so let's see. Are you seeing this? Yeah, probably. So one of the things that you see is the cut. So Carla, maybe what you're seeing is the cut because the atom comes out in and off of the layer. Huh? This is this atom that you see that disappears. This is because of the periodic boundary conditions. So don't pay attention to this because it's not thing. Then for the rest, yeah, there are some changes and we cannot tell for how thick these changes are. I mean, probably we could go and investigate a little bit more on this, but this we haven't done, okay? But the atoms appearing and disappearing, this is a problem of the plotting, that we fix the box, but the atoms can move inside and outside. I'm sorry for that.
So maybe I can ask then about the p-block elements analysis. Did you find these sulfur, selenium, or I don't even know how to like, are those elements stabler or less stable than oxygen under reducing conditions?
That's a very good question. Actually, sulfur is stable at the conditions that we were working.
Oh, okay.
Sulfur is stable. The oxygen, you have seen the whole problem, but it leaches out. So when they were synthesizing the material, they were putting lots of sulfur, and in the final material, so in the material that was finally stabilizing the production and where these measurements are taken, the amount of sulfur was relatively small. Mm-hmm. So it's much less than initially in solution, and that initially in the preparation system. The same is for selenium and tellurium, and actually tellurium goes away much faster. Actually, they didn't like to do the experiments with tellurium because it seems that it's not so nice to have it in the lab.
Mm-hmm. Interesting.
But I think Gaston can comment on those because he was also probably close to them when they were done.
So there's another question on the ND, so from Aziz. And the question is, does the segregation of the copper 0 state have any influence in the catalysis?
The segregation, you mean in the dynamics, I assume?
It says in the MD analysis.
Yes, so the thing is, we need to go into all the details because we think that we can, because we only characterize the different ensembles. But we think that now what we could do is, now that we have these ensembles, calculate the different populations for these ensembles. And we think that this segregation would be close to a model for a grain boundary. And maybe we can, if we could map these to the different preparation systems, if the system is more resembling a grain boundary or a different type of preparation, or a pitting, I mean, trying to make a hole in one of the surfaces. We truly think that the different populations of these different ensembles will be the final responsible for the reactivity found.
I was just wondering, do you consider any kind of potential controller charging in your MD simulations?
Unfortunately, not.
Okay.
But if we have ways to do it, we would be extremely happy to work with you and check it.
Yeah, we would love for that to be possible as well. Yeah.
Because yeah, I mean these calculations, they need to be seen as a, you know, as a potential way to go to see if there is something else. Mm-hmm. With typical ensembles that we are calculating for other surfaces. And missing the potential, missing the solvent, and missing the electrolyte, that's a little bit of a pain, I have to say.
Yeah. Okay, so have we any further questions? Is this your chance? Okay. All right, so in that case, thank you so much again, Nuria, for that really.
Thank you.
Yeah. So
and keep on with this very nice list of seminars. Thank you.
Yes, thank you.
Thank you.
Yeah. All right, it was really great to see all this work. I've never seen this from you before. So thank you. Yeah. All right.
Thanks, everyone, and see you next week.
Okay, take very good care.
Yeah.
Thank
Bye-bye.
you.
Ciao.
Ciao.
I am still recording. How do I stop all this? Oh my God.
You have to just.
No, I'm just.
Are you still recording? Okay.
Yeah. Just
oh yeah. Stop recording.
End.